eventually the first talk of this afternoon session is by Timur Nasybullov from the Sobolev Institute of Mathematics, Novosibirsk State University. And his topic is virtual knots and representations of virtual braids. So it's to you, Timur.
Thank you, Sophia. First of all, good afternoon, dear friends. First of all, I would like to thank the organizers for giving me an opportunity to give a talk here. Unfortunately, I was not able to attend previous days of the conference since I was on another conference in the Kazan city, and I wonder how Andrei Vesnin was able to participate both of them. So he was waking up at 6 o'clock and was listening talks here and then come to the conference in Kazan. It's impossible for me, so I joined just right now. Second, I would apologize, like a part of this talk I was giving during the conference called Geometry Days in Novosibirsk. So for some of you, not for all of you, but for some of you, some of the results introduced in the talk would be like familiar, but it's not the same talk. So I added some results. So today I'm going to speak about virtual knots and representations of virtual braids, and the majority of my talk will be devoted to representations of virtual braids. So let us start. And we will start from the definition of the classical braid group, which is familiar to all of us. The virtual braid group on n strands, which is denoted by Bn, is the group which can be given by generators and relations in the following form. It has n-1 generators, sigma 1, sigma 2, and so on, sigma n-1, and it has two families of relations which are depicted on this slide. The first family of relations is so-called Farr commutativity of generators. If the difference between indices is large enough, then they commute. The second family is this family of relations. It is so-called the long relation of the braid group, and it holds for all indices here. And these groups were introduced by Artin as a tool for working with classical knots. Later, Louis Kaufmann generalized the notion of the braid group to the so-called virtual braid group. So the virtual braid group, which is denoted by VBN, where n is the number of strands, also can be given by generators and relations in the following way. So it has two n-2 generators, sigma 1, sigma 2, and so on, sigma n-1, and new generators, rho 1, rho 2, and so on, rho n-1. And it has lots of relations which are depicted here. So I will underline that the first two families of relations are relations of the braid group. Then three families of relations are relations of permutation group. So if we identify the generator rho I with the transposition of with the transposition which changes I and I plus 1, then these relations are exactly the defining relations of the permutation group, the full symmetric group. And then two families are so-called mixed relations of the virtual braid group, which involve both generators sigma 1, sigma 2, and so on, sigma n-1, and these generators. So, and if in the virtual braid group we generate a subgroup by these generators, sigma 1, sigma 2, and so on, sigma n-1, then we will obtain exactly the classical braid group. And if we will generate a subgroup by these generators, rho 1, rho 2, and so on, rho n-1, then we will obtain the full symmetric group. So it means that the virtual braid groups on n strands is generated by two subgroups, classical braid group and the permutation group. Yeah, but of course they are connected by these relations. And these groups were introduced by Louis Kaufmann in his famous paper about virtual knot theory. And yeah, it was a convenient tool to work with virtual braids. So, and since here we are on the conference devoted to knot theory, I will say some words about geometric interpretation of virtual braids, which is written here. So for let us fix the number n, and for a for an index I which changes from 1 to n minus 1, denoted by sigma I and rho I is exactly the same letters as we had on the previous slide, the following pictures. The first picture is a configuration of n strands. Almost all of them go just from top to the bottom, and the strands with number I and I plus 1 intersect each other such that the strand with number I plus 1 goes over the strand with number I. It is the picture for sigma I. And the picture for rho I is this picture. It's more or less the same, but here we have a specific type of crossing. And one can multiply such pictures. So in order to multiply two such pictures, just one has to, in order to find the product alpha beta, we need to write a picture beta under the picture alpha. And as an example, I draw here a picture which is the product rho 1, sigma 2, sigma 3, rho 2. A short comment, like rho 1, the letter rho means that we will have this type of crossing. 1 means that this crossing will be between the first and the second strand. Sigma 2 means that we will have the classical crossing. The letter sigma means it. Here you see classical crossing. And the index 2 means that the second and the third strand will intersect, and so on. So, and such pictures, they are called virtual braids, since they look like braids. And such pictures with such multiplication form a group, which is a virtual braid group, which was introduced on the previous slide by generators and relations. The identity braid in this group is like just a group where all n strands go strictly from top to the bottom. And the inverse to the braid sigma I is a braid which looks like sigma I, but the crossing here is such that the strand with number I goes over the strand number I plus 1. And the product sigma I inverse equals 1. This equality means exactly this picture, that we just can put these strands far from each other. So now we have two options how to work with the virtual braids. First one is using generators and relations. It's not very convenient because this group has lots of relations. There are like how many? 9 families of relations. It's quite difficult to work with such groups. And the second one is the way to work with these groups using pictures, which is also not very convenient. Of course, it depends on the context, but it's not very convenient since these are pictures, so it's quite difficult to manipulate with pictures. And there is a way how to work with virtual braids, is construct representations of these groups into some groups which we understand. And here I want to introduce an example of the representation. It's kind of the most famous representation, so-called Artin representation, and let me tell about it. So let Fn be a free group with n generators, x1, x2, and so on, xn. So one can construct a map phi with index a, which map generators sigma 1, sigma 2, and so on, sigma n minus 1 of this classical braid group to automorphisms of the group Fn, which are given here. This means that the image of the generator sigma I is an automorphism of the free group, which acts on all generators of the free group except xi and xi plus 1 identically, and on these generators it acts like this. So, and this map, which sends generator sigma I to this automorphism, can be extended to a representation of the braid group, and this representation is called the Artin representation, and it is known that this representation is faithful. It has a trivial kernel. And of course, since the braid group is a subgroup of the virtual braid group, then it is naturally to ask if it is possible to construct a faithful representation of the virtual braid group, and it is natural to try to extend the Artin representation from the braid group to virtual braid group, since one belongs to another. And of course it's done. There is a so-called extended Artin representation, which acts on a generator sigma 1, sigma n minus 1 using the same way as the Artin representation acts on generators of the classical braid group, and on representations rho 1, rho 2, and so on, rho n minus 1, it acts in this way, and it's again very natural because, as I already said, generators rho 1, rho 2, and so on, rho n minus 1 generate the symmetric group inside the virtual braid group. That's why this automorphism just permute generators. So this automorphism is called the extended Artin representation, but unfortunately, this representation is not faithful, and it's quite far from the faithful. It has a big kernel. So, in using years, different authors studied representations of virtual braid groups, trying to extend the Artin representation in such a way, to obtain a faithful representation. So, and here I write several papers which are devoted to representations of the virtual braid group. It's not really important like to read the title of these papers, but yeah, I just wanted to show that there are papers devoted to this topic, and here you see all the representations are representations to the automorphism group of some group which is close to the free group, like free group, free product of the free group and the free abelian group. And all of these representations were obtained like by hands, but there is a way how to construct new representations from the so-called Young-Baxter equation. And let me explain what is this Young-Baxter equation. Let X be a set and S be a map from the direct product, direct square X to itself. Then this map, we say that this map S satisfies the set theoretic Young-Baxter equation if it satisfies the following equality of the maps from x cube to x cube. Yeah, and it's quite clear how this map, for example, S cross identity, acts on the cube of x. It acts like S on the first two components, and then it acts identically on the third component. So, and in this situation, if S satisfies the set theoretic Young-Baxter equation, then we say that S is a switch on X. And as a simple example, we can show this example. So if X is not just a set, but a group, so a set with a group structure, then the map which acts in this way, like it sends a couple of elements X and Y to this tuple, it's clear that this map is a switch. In order to check, just put it to this equation and check. Yeah, this name switch, it's not the name which I create. I found it in the paper. Yeah, and I connected with that, like with the fact that this switch S, it moves a couple of elements X and Y to another elements. And if we depict it like here, so on start we have two elements, then S acts somehow on them, and then we obtain two different elements. It's kind of switch from XY to X tilde to Y tilde. So if a switch is identity, so if we look to the square of a switch and obtain an identity, then we say that this switch is involutive. So, and as I said, there is a way to construct representations using switches. How to do it? So, let X be an algebraic system. Yeah, for simplicity, we can say that this algebraic system is a group, for example. And this algebraic system has exactly n generators, x1, x2, and so on, xn, exactly n. And so let S be a switch on this algebraic system such that we can write it like this. Every switch can be written like this. So the image of the couple AB is a couple of elements, and the left element is denoted by SL of AB, and the right element is denoted by SR of AB. So it's just a denotation. The left element is denoted by this symbol, the right element is denoted by this symbol. So for I going from 1 to n minus 1, one can define two maps from the set of generators of the algebraic system X to this algebraic system itself. How does this maps? How do such maps act? The map Si acts only on the generators Xi and Xi plus 1. It sends the generator Xi to this SL of Xi and Xi plus 1, where SL is this map. And it maps the generator Xi plus 1 to the right part, SR of Xi and Xi plus 1. And the map Ri just change these elements. So these maps for all I from 1 to n minus 1, these maps are just maps from the set of generators of the algebraic system X to the algebraic system X. If we define something on generators, then quite often it is possible to extend this not from the just set of generators, but to the whole algebraic system. So, and if for I going from n to n minus 1, the maps Si and Ri induce automorphisms of this algebraic system X, it's not always happens, but it's possible that it happens. Then the map which sends sigma I to Si and rho I to Ri, then this map can be extended to the homomorphism from the virtual braid group to the automorphism group of this algebraic system X. Again, what this method allows us to do? It allows us, if we have an algebraic system X with exactly n generators, and if we have a switch on this algebraic system, then we can construct a representation from the virtual braid group to the automorphism group of this algebraic system. And as an example, I want to show you one example. Here you see just remembering like what how this method works. And if we take as X just the free group on n generators, and as a switch we have this switch which I showed you as an example, then applying this method from the previous slide, here you see SL of AB is the left part, AB A minus 1. Here the right part is A. If we apply this method, then we will obtain this result, this representation. And this is exactly the extended Artin representation. So at least the extended Artin representation can be obtained from the switch on the group X using this method. However, this method doesn't allow us to construct a lot of representations, since in order to apply this method, we need to have the algebraic system with exactly n generators. So, and as we showed, the extended Artin representations can be obtained using this method, but all the known representations which are not the extended Artin representation, like this representation, all of them, they cannot be obtained using this method, since the group where we act, this group, it cannot be generated by n elements. Here you see we need 2 n plus 1 elements, here we need n plus 2 generators, and so on. So, and what I would like to tell you is how to generalize this method, how to obtain automorphisms from switches, to some more general method of constructing representations of virtual braid groups. So let us start. And the first slide, which I will show right now, is not difficult. I want just to show one identification which I'm going to use. So let X be a set, an arbitrary set, which has m subsets, x1, x2, and so on, xm. These subsets are arbitrary. So, and imagine that we have two elements, a and b, from the direct product x times x1 times x2 and so on times xm. These both elements belong to here. Then we can identify the tuple AB with this tuple. So first we write the first elements A0, B0, like first element from A and first element from B. Then we write the second elements A1, B1, first element from A, second element from A and second element from B, and so on. So rewriting it, we can identify this set, the set of ordered pairs of ordered n+1 tuples with this set, just playing with indices. And yeah, of course, for each n we can do like this. It's an obvious notion, obvious remark, but why do I do this remark? As I already told, a multi-switch, a solution of the set theoretic Young-Baxter equation, it is a map from a square of some element, of some set, sorry, to the square of this set. Since I can identify this set with this set, I can speak about solutions of the Young-Baxter equation, or about switches, not on the squares of some sets, but on such sets. That's why I did it. And now I will introduce the definition of the multi-switch. So imagine again that you have a set X and M of these subsets, X1, X2, and so on, Xm. And imagine that you have a map S, which acts from this set to itself. Then this map is called M+1 switch. Here M+1 means that we have here M+1 components. It is called M+1 switch on X. If it is a switch on this set, it satisfies the set theoretic Young-Baxter equation, and it is a switch of very specific form. How it acts? So the value of S on the arguments C0, C1, and so on, Cm, where C0 belongs to X, C1 belongs to X1, and so on, Cm belongs to Xm, is equal to these elements. And what is written here is that the first component, which belongs to X, it can depend on all of these arguments, because yeah, X1, X2, and so on, Xm are subsets of X. That's why we allow the first component depend on all arguments, but all the next are just depend only on the corresponding component. Yeah, and this S0, S1, and so on are just some maps. So again, M+1 switch is a switch of such form. Okay. So, and we need also a definition of the virtual M+1 switch. It's a couple of M+1 switches on X. So imagine that we have two M+ switches on X, S and V. So the pair S and V is called a virtual M+1 switch on X. If the second switch is involutive, its square is equal to identity, and this relation holds. This is a relation which connects these two M+1 switches. So this is an M+1 switch. And what is the main result I wanted to tell you about is how to construct representations of the virtual braid group using these M+1 switches. So let X be an algebraic system. For simplicity, we can assume that it's just a group, but yeah, in general, it can be any algebraic system, Wandel, Wandel, vector space, and so on. But yeah, we can imagine that it's a group. So let X be an algebraic system with this family of generators. It's a big family of generators. Here, you can think about this family of generators as about set, like you have n generators, then again n generators. It's like all the family of generators can be divided into blocks with n generators. Here we fix I equal to 0, we have n generators. Then for I equals 1, we have n generators again, and so on. So it's a family, it's a big family of generators. So denote by xi the subsystem of X generated by the elements xn, x1i, x2i, and so on, xni. So fix the upper index and denote by xi a subsystem of X which is generated by these elements. So, and imagine that we have a virtual M+1 switch on X. If you remember that the virtual M+1 switch is a couple of M+1 switches, S and V, and they act from the direct product X times X1 times X2 and so on times Xm. Here we have X and we have X 1x2 and so on xm. So now using this algebraic system x, using these subsystems x1, x2 and so on xm, and using this m+1 switch, we can construct a representation of the virtual braid group. How to do it? So for j equals 1, 2 and so on n minus 1, denote by fj the following map from the set of all generators of the algebraic system x to x. How will it work? Yeah, here the formal definition is written, but yeah, I will explain it informally right now. How the map fj acts? It acts only on the generators with sub-indices j and j+1. So it means that if we understand the set of generators of the algebraic system X as like the set with blocks of length n generators, then again n generators, then again n generators, then the map fj acts on the generator with number j and j+1 in each block. It's kind of this. And these maps S, they appear from the switch S here. We can do the same with the multi-switch V here and denoted by JG. So what did we do? We had an algebraic system X with a big family of generators. We had a multi-switch M+1 switch on this algebraic system, and using this M+1 switch, we have defined a map from the set of generators of this algebraic system to this algebraic system. So we have constructed a map from the generators of algebraic system to this algebraic system, and since something is defined on the generators, quite often it's possible that it can be extended to the full algebraic system. It's not obvious. It's not always possible. It is obvious, but it's not always possible. However, sometimes it's possible. And what we proved with Valery Bardakov is that if for all j, for all indices from 1, 2 to n minus 1, the maps which I introduced before, these maps are quite, let's say, technically formulated. But if they induce automorphisms of this algebraic system X, then the map phi with indices S and V, which map the generator sigma j to fj and the generator rho j to gj, where these are generators of the virtual braid group, then this can be extended to the representation of the virtual braid group. So this theorem gives a way how to construct by an algebraic system X and an m+1 switch on this algebraic system a representation of the virtual braid group by automorphism of this algebraic system. And what is nice is that this theorem, this method, allows us to construct all representations from these papers, which I showed you like before. So all the known representations can be obtained using this method, of course, with appropriate algebraic system and with appropriate m+1 switch on this algebraic system. Yeah, now it was, let's say, quite general explanation of this method, and there were a lot of indices and maybe quite difficult to understand, since yeah, there are lots of letters. I will show you an example of this method, since this example gives a new representations which solves one unsolved problem. So now we will apply this method, which I just right now introduced, to construct a new representation of the virtual braid group. So let X be a group and the X1 be a subset of X. Yep, maybe subgroup of X. Okay. So let we have two maps S and V from x squared times x1 squared to x squared times x1 squared, and these two maps S and V are explicit and are given by these formulas. The first formula, the second formula. Yeah, just checking the definition, it's quite easy to see that this couple of maps form a virtual two switch on X. You see the first two arguments here, first two depend on all, first two values depend on all arguments, and the second two depend only on the second two. Here the same. So this couple S and V is a virtual to switch on X. So we can try to apply our method. So take a group X to be explicit. So let X be the free group with two n generators. X1, 0, X2, 0, and so on, Xn, 0, X1, 1, X2, 1, and so on, Xn, 1. Two n generators, two blocks, each of them is has n generators. So denote by X0 this subsystem of X, just a subsystem which is generated by these elements, and by X1 the subsystem of these elements. And now let us try to apply our method, and if we apply it, then we will have this representation of the virtual braid group by automorphisms of the free group on two n generators. This representation sends the generator sigma I to the automorphism of this group, which acts like this. Yeah, here xi is xi with index 0 and yi is xi with index 1. This generator. It's the new generator which which is in U and constructed by this method. And what is nice is that this representation solve one problem which I will speak about right now. So first, for this representation, which is given using this formula, we have that it sends the square of each generator. It just sends it to the identical automorphism of the free group on two n generators. It means that this representation is not just a representation of the virtual braid group, but it is a representation of the flat virtual braid group, where flat virtual braid group is this quotient. Also, note that using just direct calculations, it's easy to see that for all I going from 1 to n minus 1, this inequality holds. This representation sends this braid and this braid to different automorphisms of the free group. So it means that this representation is the representation of the flat virtual braid group, which doesn't preserve the forbidden relation of the virtual braid group. And it means that it solves an open problem from this list of open problems. And this problem was asking, does there exist an automorphism of the flat virtual braid group by automorphisms of some group? Does there exist a representation of the flat virtual braid group by automorphisms of some group, which doesn't preserve the forbidden relation of the virtual braid group? The answer is yes, it exists, and we can show it explicitly. Yeah, what is nice is that this result was obtained by a very big group of people. So here you see some familiar names in this audience, but others are students, and we obtained this result during one project which we made with the students. So what we have right now is that there is a way how to use solutions of the set theoretic Young-Baxter equation to construct representations of virtual braid groups, and using this method we are able to construct representations which solve some problems. What is nice is that usually people which study solutions of the set theoretic Young-Baxter equations and people who study representations of virtual braid groups usually are different people, because Young-Baxter equation appear in mathematical physics, but virtual braid groups appear in topology. So it means that these people mostly don't intersect, and now using this method we can take the results of the work of one people and apply it in the work of another people. For me, it's always nice to construct such bridges between sciences. So, and it was the first part of my talk, the first and the biggest and the most important. And now, since we are on the conference, which is called Knot Theory and Applications, I want to apply these results in knot theory, more specifically in virtual knot theory. So, virtual knot theory was introduced by Kaufman in this paper, and the main objects which are studied in this theory are virtual knot diagrams, and here I give a definition. What is it? So a virtual and component link diagram is a regular embedding of n circles into the plane such that each crossing is either classical or virtual. I will not stop on this definition and will not speak a lot of words about it, since majority of you know what is it. Here I show some examples which give intuitive understanding what is a virtual link diagram. A virtual link diagram is something which looks very similar to classical link diagram, but here some new types of crossings can appear, and these types of crossings are called virtual crossings. And on the set of virtual link diagrams, one can build an equivalence relation by this rule. We will say that two virtual link diagrams are equivalent if one of these diagrams can be transformed to another one by a finite sequence of the following moves, which we will call generalized Reidemeister moves. So, generalized Reidemeister moves contain like 3 classical Reidemeister moves, then 3 virtual Reidemeister moves, which are obtained from the classical by changing the type of crossing, and 1 mixed Reidemeister moves. So, and we will, if we have a virtual link diagram, then the equivalence class of this diagram by this equivalence relation is called the virtual link. And like one of the main, not one of the main, but the main object in virtual knot theory is virtual link. Of course, these links, virtual links, they have geometric interpretation. It's not just diagrams with an equivalence relation. And here I want to say a couple of words about this geometric interpretation. So imagine that we have a surface. Here I draw a torus. And it's not just a surface, but it's a thickened surface. So we multiply the surface by an interval. It means that we can put something inside of this surface. And inside of this thickened surface, let us consider some link. So here I draw something. Draw some link inside of this surface. So here we have just 2 classical crossing, and this is not a crossing, it's just one strand, this one. It goes on the back side of the surface, and this strand goes like on the front side of the surface. And if we project this link inside the thickened surface to a plane, then we will obtain a kind of this picture. So here the projections of these crossings, which are classical crossings, are exactly classical crossings. But here, in general, this strand and this strand, they don't intersect. However, their projections intersect, and it's impossible to remove this intersection. So that's why we just write here a virtual crossing. What does it mean? It means that a virtual crossing is not really a crossing. It's kind of defect of projection of the virtual link diagram to a plane. So that is an intuitive definition, or the intuitive meaning of the virtual crossing. That's why it's called virtual. It's not really a crossing. It's a defect of depicting a diagram of the link inside the thickened surface to a plane. So, and it gives away how to construct a virtual link diagram by the diagram in the thickened surface. But it's also possible to go back from the diagram to a link in thickened surface like this. If you see a virtual crossing, then you can add a handle body to a surface and put one strand through this handle body, and another one is below it. This is the geometric meaning of virtual links. Virtual links are links in thickened surfaces. Yeah, there are some details that you can, the surface is not uniquely defined. You can add or remove handle bodies from this surface. So, and we saw that virtual braids have geometric interpretation like this, and for each virtual braid, one can construct some virtual link just looking to the closure of this braid. Just connect the first top point with the first bottom point, and second top point with second bottom point, and so on. So for each braid we can construct a circle. Also the opposite is correct. So for each virtual link one can construct a braid such that the closure of this braid is equivalent to this link. So it means that from some sense to study virtual links and to study virtual braids is more or less the same, and yeah, different researchers use different approaches. The people like me who prefer to work with groups work with braids, while the people who prefer to work with pictures prefer working with diagrams. And in order to introduce you the main result about virtual links, I have to recall you what is a bike Wandel. Here I wrote the complete definition, but it's not necessary to read it completely. There are some important moments. So what is a bike Wandel? Bike Wandel, which I denote by BQ, is an algebraic system with two binary algebraic operations. First one is denoted by this symbol, and second one is denoted by this symbol. And these operations satisfy like a family of axioms which can be checked just by hand. So a bike Wandel is an algebraic system with two algebraic operations which satisfy some axioms. It's enough for us. So, and now let us connect the result about representations of virtual groups with virtual links using bike Wandels. So we know what is a multi-switch, an M+1 switch, which I introduced some time ago in this presentation. So let S be an M+1 switch on some set. It means that we can write S on a couple of two elements, S of AB, in such form. The left part is denoted by SL of AB, the right part is denoted by SR of AB. So now, on this set, let us introduce two algebraic operations. The first one, which is denoted by this symbol, is the left part of this expression, and this one is the right part of this expression. So we have a set with two algebraic operations. And yeah, I said a couple of words about bike Wandels. And if this set with these two new algebraic operations is a bike Wandel, that it depends only on the switch S. Then we call the switch a bike Wandel multi-switch. That's all. By a set and a switch, we construct two algebraic operations. If this set with these operations is a bike Wandel, then we call this switch bike Wandel multi-switch. So, and now I will introduce you the main result. So again, let X be an algebraic system with this amount of generators, and denote by Xi the subsystem of X generated by these symbols. Is exactly the same as we did with the representations of virtual braid groups. And imagine on this algebraic system we have a virtual multi-switch. We know, it was the first part of my talk, that one can construct a representation from the virtual braid group to the automorphism group of this algebraic system. So now denote by this symbol X. X is an algebraic system. Two indices S and V are from a virtual multi-switch, and beta is some braid. Denote by this symbol is the quotient of the algebraic system X by the relations this. You see, this is representation. The value of the representation on some braid is an automorphism. So since it's an automorphism, we can act on some generator, and we write that the value of the automorphism on some generator is equal to this generator. So, and we denote by this symbol the quotient of the algebraic system X by these relations. And what we proved is that if S and V are bi-Wandel multi-switches, then this algebraic system depends not on the braid beta, but on the closure of the braid beta. So it means that if two braids have have the same closure, then this algebraic system for different braids will be the same. It means that if we have a diagram, virtual link diagram, then for this link diagram, we can construct a braid such that the closure of this braid is equivalent to this diagram. Then by this braid, we can construct an algebraic system SV of beta. And from this theorem, it follows that this algebraic system doesn't depend on beta, but it depends on the closure of beta, but the closure of beta is D. It means that by the virtual link diagram D, we can construct an algebraic system X SV of D, which is an invariant for virtual links. So this method of constructing representations of virtual braid group allows us to construct invariants for virtual links. So, and this is the last, let's say, big slide of this presentation, and I want to finish asking one question which I saw in one paper, which is not my question, but which interests me a lot, and it is connected with representations of the virtual braid group and with the geometric interpretation of virtual links. I will formulate this question and stop here. So let H be a group with generators H1, H2, and so on Hm. So it's just finitely generated group with M generators. M is arbitrary, just important that it is finite. And imagine that we have an automorphism, a representation from the virtual braid group to the automorphism group of this group H. So this representation phi, we call it virtually symmetric if for any generator rho I of the virtual braid group, the image of this generator, which is an automorphism of H, just permutes these generators. The question is, this question was formulated by Bardakov, Nishidim, and Singh. Singh is Manpreet Singh, who I believe is always sitting in this conference. Yeah. The question is, does there exist a representation of the virtual braid group which is not equivalent to a virtually symmetric representation? Of course, the authors of this question expected that no, it doesn't exist. And I also think that it doesn't exist. Yeah, the authors of this question prove that the known representations are equivalent to virtually symmetric. I also believe that the answer to this question is negative, and I have two reasons why I believe it. The first one is that the generators rho 1, rho 2, and so on, rho n minus 1 generate the symmetric group and the virtual braid group. Sorry. It means that these generators should kind of permute something. Maybe if we choose generators correctly, these generators will permute these generators. So it says exactly this. And the second is more intuitive. Why I believe that the answer is to this question is no, is the geometric interpretation of virtual braid groups. What is the meaning of the virtual crossing? Virtual crossing, as I already said, is not really a crossing. It's the effect of depicting strengths on the plane. Here you see it. It means that these strengths don't really intersect, and in some sense they don't affect each other. But generator rho I is exactly about virtual crossings. It means that in this generator, these strengths also kind of don't affect each other, and that's why, yeah, it seems like these strengths just should cross and, let's see, permute with each other. Yeah, that's all I wanted to tell you. Maybe the last part was a bit kind of on the level of intuition, but it makes me to believe that the answer to this question is no. Here I thank you.
Okay, let me find in the reactions, yes, the right thing. Thank you very much
Thank you.
For this very interesting talk, Timur. Are there any questions by the audience?
I see one in the chat. Here it's written. Oh, I will read them and try to answer. The first one is a question from King Lan, and he writes that representations of braid groups, I think classical braid groups, can be obtained from any object in a braided fusion category using the braiding. Can they be extended? I believe that extended to representations of virtual braid, to the virtual braid group, from classical braid group to virtual braid group. It depends on the representation. So since the classical braid group is sitting inside the virtual braid group, then so the answer is like this. I don't know, but I never met a representation which was impossible to extend from the classical braid group to the virtual braid group. This is the answer to the question: is it possible to extend representations obtained using braiding? Is it okay? Yeah,
I guess we can just simply define the image of the row I to be switching instead of the braiding. So I think this is somewhat clear.
Yeah, maybe we can indeed define the value on generator's row I, just switch, and it will be the extending.
If this is true, then there may be plenty of representations coming from those braided fusion categories, I think.
Seems like, yeah, but I never met these representations. But yeah, seems like if there are plenty of representations of braid groups, then there are plenty of representations of virtual braid groups. But it's important that such representations should be, close, at least close to faithful. Because if these representations which we try to extend are not faithful, then it doesn't have any sense to extend them.
Thank you.
Then I see another question in the chat. There are two from Anderson Vera. I believe that I was a student. I have visited a conference called Winter Braids in France, and maybe I was living in the same room with Anderson. I'm not sure because I was living with the guy called Anderson Vera. So he writes, I have a couple of questions. First, is there a symmetric way of finding multi-switches? No. It's multi-switch is
way, yeah?
systematic. Sorry, symmetric. I read there. Systematic. I don't know such a way. All the multi-switches which we found, we just got some switch and tried to generalize it, but all of this our tries were, some creative. So we didn't find a unique procedure how to construct a multi-switch from a switch. We just used some, intuition and some findings, some lookings. Yeah. If you find this way, yeah, you will find a way how to construct new representations in an easy way. So, is there an analogous generalization to quasi-triangular Hopf algebras? Yeah, I have heard about quasi-triangular Hopf algebras, but I never worked with them. That's why I cannot answer this question, because this object is not very familiar with me. I believe that, sorry, here I will not even try to answer, because the object, quasi-triangular Hopf algebra is not very familiar with me. So that's all. Yeah. Thank you, Anderson.
Maybe Valery is more apt, appropriate to think and answer such a question. Bardakov. Are there any other questions? Okay, so more questions privately to the speaker then. And let's thank Timur once more.